For this lesson, we'll be focusing on the DC analysis of field effect transistors, also known as FETs. Now for the official definition, FETs control the flow of charge carriers from the source to the drain by a potential applied to the gate electrode. Now in the illustration below, I have a picture of a BJT next to a FET. Reason being is because they actually share similarities as well as common ground. The collector acts as a drain, the base acts as a gate, and the emitter would act as a source. The only difference between these two components is the BJT is a current control device and a FET is a voltage control device. Hence why a FET is also used in amplifiers as well as switching applications. So let's jump right in of how a field effect transistor works. Well, the good news is it's pretty straightforward just based on the node names. If you look at the drain and the source, you'll see that current is either flowing to the drain or from the drain, or to the source and from the source, based on the two different channels we have, our P channel and our N channel. And then you have the gate in the center, which in a sense is either pitching off or closing that channel and controlling your current flow. Just like BJTs, FETs also have differing operating regions. However, they're named slightly different as well as how they operate. The first one we'll look at is saturation or constant current region. This is when your drain current reaches its maximum value. This is typically when you want your FET to act as a switch or act as a relay in this case, because it's either you want your current to be 100% or 0. Your next region is linear. This is when your drain current displays a linear or quadratic response based on your drain source voltage. If you look at the illustration below, in the green area, that's your linear region. That's when you see those lines actually have a linear response or a quadratic response. They're sloping upward. Your next region is your cutoff region. This is when your drain current is 0. In other words, your transistor is off. Your last region is your breakdown region. This is typically when you have a channel breakdown or possible damage to your FET. So before we move forward, let's go over a few terms. Your drain current, that's your current that flows through the channel of your FET, typically from your drain to your source if it's an N channel, and vice versa if it's a P channel. Next, you have your drain voltage. That's your voltage supplied to your FET. It's usually at the top of your circuit, indicated by VDD. Next, you have your gate source voltage. That's a main parameter you need to know when determining your drain source current. The reason it's important to know because your next term, you have gate source cutoff or pinch off. That's the value of your gate source voltage that cuts off your transistor. In other words, it makes your current 0. Next, you have your shorted gate drain current, and that's when your maximum possible value of your current can be. Lastly, you have your drain source voltage. That's the second parameter that affects your drain current when in the linear region. Now just be aware, your gate source cutoff and your shorted gate drain current, those two items are typically given on data sheets. So anytime you do problems, it's very common you'll actually have those provided to you. Now this is where we get into the weeds a little bit. FETs actually have various different types. And depending on which reference material you have, they usually just break them up into 2 subtypes. However, there are much more than just these 2, but I'm just going to go over the most common ones for now. The first category is your junction FET, your JFET. They're very easy to identify and they usually have two different symbols. Next, you have your MOSFET, which is your Metal-oxide-Semiconductor FET. Be aware, some of your reference material may also say your insulated gate FET, but I'm just going to call them MOSFETs just to keep it simple on myself. Now in those categories, those are broken up to 2 subgroups, which is your depletion MOSFET and your enhancement MOSFET. The thing to be aware of is how they're symbolized. So keep in mind that's what this main slide is for, is to let you know that there are 2 different symbols for JFETs, depletion MOSFETs, and enhancement MOSFETs. Now, as stated in the previous slide, MOSFETs are broken up to 2 different categories, depletion and enhancement. But the good news is your depletion shares a little common ground and overlap with your JFETs, that common ground being your equations. Reason being is your depletion means the drain source path conducts when your gate source voltage is equal to 0. Now, unlike depletion, enhancement means your drain source path does not conduct for a gate source voltage equal to 0. So what does this mean? It means these MOSFETs are actually ideal for logic devices. if you utilize your microprocessor with these MOSFETs, you can use these FETs as a switching device or a relay in a sense. You can apply 5 volts to the gate to operate this MOSFET. Now what this also means is you can utilize the depletion and JFET equations with only a few exceptions. One being enhancement MOSFETs utilize a conductivity factor, which is indicated by K, and that you use that when you want to determine your drain current. Now K is measured in amps over voltage square, and again your equation is given at the bottom. Also, your gate source cutoff or your pinch-off voltage, VP, is defined as threshold voltage or VT, and you'll see these on all your data sheets. And since we're performing a DC analysis, just like BJTs, we're going to be following the same steps. We're going to remove our AC components, which means we're going to remove our capacitors and our AC sources. The reason you move your capacitors is because the active opens when performing a DC analysis. Next, you're going to simplify the DC circuit using Thevenin if necessary. Next, you're going to calculate your parameters as required. Now the good news is a lot of these steps are going to be similar to the BJT, so if you got really good with those, this is going to be easy overlap. Also, be aware of how the subscripts look with some of these equations. They're all capital letters. Capital letters means that it's going to be a DC analysis. Any time you see lowercase, that's an AC analysis. All right, let's jump to a good example problem. For this one, I provided a gate bias JFET, and this one, we want to determine the drain current for this in-channel JFET. Pretty easy. Now, we already provided the gate cutoff voltage as well as your shorted gate drain current. And these particular items can be found on my data sheet, so this is not exactly uncommon to get these provided to you. Now, following the rules that we stated in the PowerPoints, the first thing we're going to want to do is remove our AC components, which means I want to remove all of our capacitors and we want to remove our sources. So I'm going to go ahead and delete those. Then I want to reduce the circuit down if possible. Well, looking at this, it doesn't look like it can be reduced down anymore. So, which means we go to the last step. So which means we use our parameters with the equations to our right to determine what we're looking for. It means we're going to be able to look for our drain current. Well, let's first establish what we know. First of all, current does not flow through the gate. So at this node, there's going to be zero current flowing through the gate, which means anytime you have a setup like this, a gate bias setup, you're not going to have current flowing through this resistor. And if there's no current flowing through the resistor, that tells you there's no voltage drop. So that means the same voltage is here would be the same voltage here. If you have a 2-volt power supply, it's going to be 2 volts up here as well. Now keep in mind, this power supply is not 2 volts. It's actually negative 2 volts if you actually took a meter from here to here as your reference point, because this is negative, this is positive. Always be aware of that when you're actually doing some of these problems, that some of these power supplies may be swapped on you. So if we have negative 2 volts right here, you're going to have negative 2 volts right there. And again, since there's no current flow, then that means that this is almost acting like this resistor is not here for the sake of this particular calculation. Now, why is that good? Well, that tells us our gate voltage. And from there, we can actually determine our gate source voltage, which is our VGS. Now, why is that good? Because gate source voltage measures between these 2 points. So if you stuck a meter between these 2 points, that would give you this value. Now the good news is, if you took a negative lead right here, that's going straight to ground. That means you're actually measuring in reference to ground instead of a resistor. So that means your gate source voltage equals your gate voltage. So which means VGS equals negative 2 volts. And I'll tell you what, I'll put it over here. Now the good news behind that, we actually have all the parameters we need to actually plug and chug in this equation right here. So let's go ahead and do that. So drain current, ID, equals, and that's going to be 12 milliamps. I'll try to work on my handwriting. Times 1 minus, and we said this one's going to be negative 2 volts. Tell you what, put our units in there. Negative 2 volts over, and we already have a cutoff provided to us, negative 4 volts. Close parentheses, and then that one's going to be squared. And all I have to do is reduce this down, simple math. So it's 12 milliamps. 1 minus. Now a negative 2 over negative 4 is going to be 0.5. And that's going to be volts squared. And that one's pretty easy. 1 minus half is still half. So it's going to be 12 milliamps times 0.5 volts. And that one's going to be square. And 0.5 square is going to come out to be 0.25. So that one's pretty easy. And that's multiplied times 12 milliamps. And that's going to come out to be a final answer of 3 milliamps. So this one was a relatively easy problem. But this is a good one to get your feet wet as far as how to understand how some of these JFETs can work and how you plug and chug in some of the simplest equations. All right, let's do another example. This one, we also will be looking at a JFET circuit. This one's going to be a voltage divider circuit. So this one we're going to use a few extra equations as well as give you a few curveballs. So for this one, we want to determine your drain current as well as your drain source voltage. So we want to know ID, and we want to know the voltage between here, which is your drain source voltage. Well, same as last time. The first thing I want to do is remove my AC components. So we're going to move all of our capacitors and our AC sources. So let me go ahead and delete those. Now you're probably wondering why I took off the load resistor. Once you disconnect that capacitor, that resistor is no longer connected, so there's no point in having it. Now the first thing I'm going to do is, same thing as the last problem, I'm actually going to look for the voltage right here. I want to look for our gate voltage. Because I always like to start there because it helps provide other parameters somewhere else. The way we can do that is using this guy right over here. This is just using a simple voltage divider rule. So right now I have a supply voltage of 20 volts, and then I have R1, which is 100K, and R2, which is 20K. So if I use this equation over here, it's going to be your gate voltage equals, and it's going to be 20 volts times, and then R2. R2 is going to be this one down here, which is 20K. Now be aware, I have my equation set up as R2 over R1 plus R2. Some of your books may have R2 up here and R1, so be aware of how yours is set up. If yours is set up the same as mine, you're good to go. Anyway, over, and this is going to be 100K plus 20K. And then close parentheses. And that's going to be 20 volts times, and this is going to be 20K over 120K. And if you just plug and chug the rest in your calculator, it's going to give you an answer of 3.333, and it's going to be repeating volts. So right there, I have our gate voltage, which I'll put over here. When it comes to these voltage divider circuits, this is one of the easier ones to figure out. So I like to start with the easy one. Go for the low-hanging fruit first. Go ahead and delete this. Now here's where the tricky part comes in, because I want to find my drain current, which is this guy right here. However, there's a few more unknowns I have. So if I bring this guy over here, your drain current, and of course our shorted drain parameter. Now you have right here your gate source voltage over your cutoff voltage. And of course square. The good news is we have this one right here, we have this one right here, but we don't have this one or this one. We have two unknowns. We have your drain current and your gate source voltage. Well, there's a way to manipulate this. You can actually substitute this guy out with something else. You can say your gate source voltage equals your gate voltage minus your source voltage. So if I was actually going to put that in there, tell you what, I'll go ahead and bring this down a little bit. 1 minus, and I'll just substitute this guy right here. So instead of VGS, it's going to be your gate voltage minus your source voltage over your cutoff voltage. Now you're probably thinking, why does that help? Because right now I still have two unknowns. You didn't help me. We still have our drain current unknown, and we still have our source voltage unknown. So we have two unknowns still. That doesn't help. Well, you can kind of substitute it one more time. For this guy right here, you could substitute this guy in here. So again, if we bring it down one more time, this is where it gets tedious. 1 minus, and this is your gate voltage, minus, and I'm going to substitute this guy right here for our source voltage. So it's going to be RS times your drain current over, and then our cutoff voltage. And close it square. So right now, I went from 2 unknowns to now having just 1 unknown, which is ID. So that's a great thing. Now we have to do quite a bit of algebra and fill in the blanks to start working this problem down. So I'll tell you right now, let me rewrite this problem one more time. I'm going to say your drain current equals IDSS 1 minus is your gate voltage minus your source resistor times your drain current again over your cutoff voltage. Trying to keep my handwriting as pretty as possible, and then square. And what I'll do is I'm going to erase all these and move this guy up. Now this is where the magic happens. This is where the fun begins. So I'm going to actually start filling in some of these blanks. So I have 14 milliamps, parentheses, 1 minus, and we know our voltage is 3.333 volts. I'm going to go out to 3 decimal places, minus, and we know our source resistance is 5K, so 5 kilo ohms. And I'm going to do one other thing. For our ID right now, our drain current, I'm actually going to say our drain current equals X for now, just to make it easy on me. So this is times X. And this is going to be over our cutoff voltage, which is negative 3.847 volts. Close parentheses and square it. Now, what I'm going to do is I'm going to actually see if I can simplify this down one more time. So I'm going to bring this down. ID equals 14 milliamps. 1 minus, and what I'm going to do is I'm going to actually divide 3.33 by this negative 3.847 and do the same thing, 5K divided by 3.847. So I'm just going to go ahead and fill that in. So it's going to be negative 0.866, and this is going to be plus, I'm going to go ahead and round for this one. I'm going to say it's 1.3K, and that one's going to be times X. Close parentheses and square. And now I want to get rid of this pesky minus sign, so it's going to be ID equals 14 milliamps again, times 1, and this is going to be plus 0.866, because a negative times a negative gives you a positive, and then a negative times a positive gives us a negative, so it's going to be minus 1.3 kilo ohms times X, and that's going to be square. Now I'm going to go ahead and add these two together, so it's going to be drain current equals 14 milliamps times 1.866 minus 1.3K times X square. And of course, this is where the fun part comes in. I'm going to actually go ahead and square this guy right here. And the way I'm going to do that is I'm going to bring it down one more time. Actually, it's going to be more than one more time. 14 milliamps. And it's going to be 1.866 minus 1.3 kilo times X times the same thing again, 1.866 minus 1.3K times X. So that's how I squared it. I went ahead and multiplied it times itself. And I'm going to see if I can do one more line here before I erase all this. So let's see, we can see if we can fit this. We're going to say drain current equals 14 milliamps times, and I'm going to do 1.866 times 1.866, which is going to give me 3.482, and then it's going to be minus, because it's going to be 1.866 times 1.3K X. It's going to give me minus 2,420, I'll just round to 6, and that's going to be X. Do the same thing again, but I'm going to multiply the 1.3K times this side. Now the good news is negative 1.3K times that gives us the same answer, so it's 24, 26X. and then 1.3K times 1.3K is going to give us a positive, because a negative times a negative gives us a positive, 1.69 meg, and that's x squared, because an x times an x gives you a square. And of course, that closes that guy off. All right, so I'm going to see if I can move this up a little bit and see if we can simplify this down a little bit more. I went ahead and shrunk this down a little bit just to make it fit. So let's go ahead and simplify this area down right here. So what I'm going to do is I'm going to go ahead and add these two x's together, and I'm going to move x squared to the front. So I'm going to make it in our typical way we're used to seeing it. So I'm going to say drain current equals 14 milliamps times, I'm going to go ahead and bring this guy first, so it's going to be 1.69 meg square, and that's x squared, excuse me, minus, and this is where I'm going to add these two guys together, and that's going to give me a negative 4,852 x, and that's going to be plus, and I'm going to bring this guy over here, which is 3.482, and we're going to close that parentheses. Looks like little by little we're making this guy smaller. So now I'm going to take this 14 milliamps and actually multiply it into this equation over here. So that way we can simplify down one more time. So I'm going to do drain current equals, and it's 14 milliamps times 1.69 meg, 23.66 kilo, and that's going to be x squared. And then we're going to have minus, and that's going to be 14 milliamps times 4,852. It's going to be negative 67.9, and we'll go ahead and say 3. Make it easy, we'll round. And that's x plus, then we're going to do 14 milliamps times 3.482, and that's going to come out to be 0.0, we'll say 49. And then the last thing we're going to do is, since we already said ID equals x, we know this guy right here is considered to be x. Go ahead and subtract ID from this side, and I'm going to subtract him from this side. So he's going to come right here and be added to this guy right here. So all I'm doing is subtracting an x and pretty much stacking it on this guy, which means 0 equals 23.66 kilo x squared. And then since I'm adding one over here, it's going to be negative 68.93 x, because I said ID is x, and then it's going to be plus 0.049. Well, now that we have that, we can actually plug and chug this guy right into our calculator as is. So what we're going to do is we're going to go to equation mode, select option 3, and then actually plug these numbers in. And looking at our calculator, it's going to give us an actual final answer of ID equals 1.231 milliamps. So that right there is this guy right there. And I'll tell you what, I'll put him to the side, that way we have it on a permanent scale. Now finding that was very tedious. It was a lot of work and it was very time consuming. However, the better you get at this, the faster it will go. Plus, this is knowing how to use your calculator. I did it the long way and pretty much showed you every nook and cranny just so you see what I did. That way I didn't skip steps. Next, we got to find our drain source voltage. That one should be pretty simple. Let me go ahead and erase all this. All right. Now the last one we want to find is our drain source voltage. And that one's actually pretty easy because now we have the parameters we need to just plug and chug it in this guy right there. And that's all we have to do. So now that we found our drain current, we can just do that. So tell you what, I'm not going to redo the whole equation. It's pretty much going to be 20 volts minus, and we have our drain current now, which is 1.231 milliamps. And it's going to be multiplied times your drain resistor and your source resistor. So it's going to be 5K and 5K. I'll tell you what, I'll just show you that I did both. Even though we can do it in our heads and we know it's 10K. So which means our drain source voltage is going to be 20 volts minus, and I plug and chug this in our calculator, is going to give us, it's going to be 12.31. And then if you subtract that, it's going to give you a final answer of 7.1 3.69 volts. And that right there is your drain source voltage. All right, let's do one last problem. All right, for our last problem, I mixed it up a little bit. We want to determine your gate source voltage, your drain current, and your drain source voltage. And this is also an N channel, but however, this is an enhancement MOSFET. So, which means our parameters are given are going to be slightly different. We have a threshold voltage, and then we have our conductivity parameter or factor. But we're going to still actually attack this just the way as we do all the other ones. So let's get rid of our capacitors and our AC voltage sources, as well as anything connected to those capacitors. We're getting rid of that guy. Now we want to determine our gate source voltage. So we want to know this guy right here and this guy. Well, there's a few ways to approach this. I'm going to do the same thing as I did on the other ones. I'm going to go for the low-hanging fruit, which is our gate voltage. And the best way to find that is go ahead and use this equation right here. We want to actually find the voltage right here in reference to ground. So between these 2 points, this would give us your gate voltage. So all I have to do is actually go gate voltage equals 10 volts, your VDD, times R2, which is 18K, over R1 plus R2, so it's going to be 32K plus 18K. And I'll tell you what, just to save a little bit of time, we'll just go ahead and plug and chug that in our calculator completely, and that will give us 3.6 volts. So we know our gate voltage is 3.6 volts. This is actually an easy way to start off. Okay, I'm going to clean this up. Now, I probably want to see if I can find our gate source voltage. That seems to be the pattern. I seem to go from there. I seem to actually work on our gate and then go from there. Well, if I use that equation, our gate source voltage, it's going to give us our gate voltage, which we know, minus your source voltage, which we don't know. So what I can do is, I can do the same thing as the last problem. I could say your gate source voltage equals gate voltage minus, and I can look at this guy right here, RVS, or your source resistance, times drain current. Now you're probably wondering, well, how does that help? Well, I can use that guy right there to substitute out your drain current. See, the last problem we were trying to find drain current. This one I want to find your gate source voltage. So which means I can go gate source voltage equals gate voltage minus, and I want to keep my resistor right there, but I'm going to substitute this guy out right here with this guy. So which means it's going to be source resistor, your conductivity factor, and it's going to be times your gate source voltage minus your threshold voltage, and that's going to be square. So right now we are back to one more unknown, which is your gate source voltage, because we have all the other ones. So let me go ahead and fill this in a little bit, that way you get a little aspect of what I'm doing here. So it's gate source voltage equals gate voltage, which we know is 3.6 volts, minus, and your resistor right there is 1K. Tell you what, see if I put an ohm there, that way you can see what I'm doing. And then I'll tell you what, I'll do a bracket right here. And we have K, which is 0.5 milliamps divided by volts square. And I'm going to take away the units pretty soon, but I'm going to at least fill this one out. Close parentheses, and this is VGS, minus your threshold, which is 0.8 volts. Close parentheses, square, and then close bracket. So it's a lot of work here, but it's not too difficult once you start working into it. All right, and the same thing as last time, I want to go ahead and switch our gate source voltage to X. So I'm going to say for right now, gate source voltage equals X. That way we can keep this clean. So which means X equals 3.6 minus 1K, close bracket, 0.5, and I'm going to say times 10 to the negative 3. And then we're going to say X minus 0.8, close bracket, square, and close bracket. Well, just like what you're supposed to do in math, let's work on the parentheses, then work our way out. So I'm going to say X equals 3.6 minus 1K, and I'm going to start working on this guy right here, which means I'm going to say 0.5, 10 to the negative 3, and then I'm going to say x minus 0.8 times x minus 0.8. What I'm doing here is I'm trying to get rid of that square. Working this down, we're going to say x equals, I'm going to say 3.6 minus 1k, bracket 0.5, 10 to the negative 3, and this is where I'm going to say x squared, and then we're going to do x times negative 0.8, which is going to be negative 0.8x, and then we're going to do this one, negative 0.8 times x, which is negative 0.8x, and then 0.8 times a negative 0.8 is going to give you a positive 0.64. And there we go. Move this over a little bit. X equals 3.6 minus 1k, bracket 0.5 times 10 to the negative 3, parentheses. And what I'm going to do is I'm going to add these two together. So it's going to be x squared minus 0.8 plus a 0.8, negative 1.6x. And that's going to be plus 0.64. And then close that up. What I'm going to do is I'm going to work on this bracket right here. I'm going to multiply the 0.5 times 10 to the negative 3 times these guys right here. That way we start getting rid of these brackets. So I'm going to say x equals 3.6 minus 1k. What I'm going to do is I'm going to just leave it as a bracket. I'm going to say it's 0.5 times 10 to the negative 3 x squared minus, that one's going to give me negative 8 times 10 to the negative 4 plus, that one's going to be 3.2 times 10 to the negative 4. And that closes that guy off. So little by little, we're able to simplify that down a little bit. Now, we can actually take this 1k here and multiply that back in. So I'll tell you what, I'm going to clean all this up and move this guy upward. Now I can multiply the 1k times this bracket. So I'm going to bring this down. X equals 3.6 volts minus, and 1k times 0.5 times 10 to the 3, x squared equals 0.5 x squared minus 0.8 x, and then it's going to be plus 0.32. Yeah, even I forget the x's every now and then. Now what I need to do is I need to get rid of this pesky minus sign right here. So what I'm going to do is x equals 3.6. I'm going to do minus times 0.5x squared is going to be negative 0.5x squared. Negative times a negative equals a positive, so positive 0.8x. And then negative times a positive is going to be minus 0.32. Now what I can do is I can actually add the 3.6 with the 0.32 over here. So x equals 0.5x squared plus 0.8x positive, and then 3.6 minus 0.32, 3.28. And just like last time, since we have the x over here, minus x, that's going to be 0 equals 0.5 squared, and that's going to be minus 0.2x, and that's going to be plus 3.28. And guess what I forgot to do? I forgot to bring down this minus sign. There we go. So with this equation right here, we're able to plug and chug in our calculator. So all we have to do is go to our mode, option 5 equation, and then option 3, and then just go ahead and plug these numbers in. And that's going to give us a gate source voltage of 2.369 volts, which we're just going to go ahead and say is 2.37 volts. And I'll go ahead and put that guy right over here. All right, that was very long and tedious. Let's see, hopefully the rest of them go a little quicker. So let me clean this up right here. Now we want to find our drain current. Well, that's pretty easy now, because now I can use that same equation right here and plug our gate source voltage right into this equation right here, and we should be able to find our drain current. So which means our K is 0.5 milliamps volts square, and that's going to be 2.37 volts minus your threshold, which is minus 0.8 volts, and then square. So that means your drain current equals 0.5, and this is going to be 2.37 minus 0.8, 1.57, and then we're going to square that and multiply it times 0.5, which means our drain current is going to be 1.23 milliamps. And it's milliamps because that got right there. So now we're able to find our drain current just by plugging and chugging our equation and finding those parameters. So put that guy over here, 1.23 milliamps. And I bet you we can use that equation right there again, because since we have a voltage divider, we can actually use this guy right here and plug and chug that right in. So same thing as last time. I'm going to say 10 volts minus your drain current. And that's going to be parentheses, drain resistance, source resistance. So I have 4K plus 1K, and that's going to be 5K obviously. And I can plug and chug that in the calculator. It's going to give me 5K times 1.3 milliamps, 6.15 volts. And then just subtracting 10 minus 6.15 volts is going to give us a drain source voltage of 3.85 volts. So just by manipulating a few equations, we're able to find all these parameters. And right now it was very long and tedious to find them all, but hopefully with this much information, you should be able to solve just about any one of these problems. But if you have any problems or any questions, feel free to let me know, and I hope you all have a good day.